Today's lesson is going to focus on combustion reactions. Combustion reactions require two very specific reactants. They require a fuel of some sort, which is typically a hydrocarbon. So based on that name, you get a sense that the fuel substance is going to have hydrogen and carbon in the chemical formula. Sometimes it might have oxygen, it might have a nitrogen as well, but we'll mostly see a hydrocarbon. It also has to have oxygen gas because the oxygen feeds the fire or feeds the fuel and feeds the combustion reaction. So you have to have two of those to recognize a combustion reaction. Fuels can be any type of carbon-based molecule, okay, but most often it'll be carbons with hydrogens in them. And combustion reactions are exothermic. Okay, this term means that thermic refers to thermal energy, which is heat. Exo refers to the fact that it is leaving. So it releases energy out into the environment in the form of heat and also in the form of light. There are two types of combustion reactions. The first is complete combustion, and then the second one is incomplete. We'll take a look at both. Complete combustion occurs when there is lots of oxygen present to thoroughly combust your fuel or your hydrocarbon molecule. So you have to have lots and lots of oxygen. And the reason that we have to have that is because when we carry out combustion reactions, just in an open system, so just out in the open, air only contains 21% oxygen, okay, which is not a lot. And so in order to have a reaction where you fully combust your fuel or your hydrocarbon, you need to have a lot of oxygen present in order to do that. When complete combustion happens, a couple of things will occur. Your products are always going to be CO2 and H2O, and that's pretty much it. The minute that you have incomplete combustion, you start to form other byproducts. But a complete combustion reaction will only produce carbon dioxide and water. And visually, you can tell that you have a complete combustion reaction because you're going to have a blue flame and you're going to not see soot being formed. And soot is this black carbon substance that we see here in this test tube. Notice here we see a yellow flame. Okay, those are all clues that you do not have complete combustion. And then over here, we notice a nice blue flame. For combustion reactions, you would not see any soot or any carbon particles. When you have complete combustion reactions, the reaction is always the same. You take your fuel. So in this case, we're going to look at methane, which is the fuel that we have coming out of the Bunsen burner taps, or a lot of you will combust this at home if you have a natural gas furnace. And you take your fuel and you react it with oxygen, and then your products are the same. You have CO2 and you have water. And from there, all you must do is balance your reaction. Okay, and with complete combustion reactions, there's only one way to balance them. With incomplete, sometimes there's more than one way that you can balance it. So you just move along and you balance your atoms so that they are equal on both sides and that you satisfy the law of conservation of mass. Let's try this one together. It says, write the complete combustion reaction for propane with sufficient oxygen. So notice the language that we use. Sufficient means, there is enough oxygen. Sometimes we'll say, a reaction with lots of oxygen, or, an extra amount of oxygen. That is all, words that are implying complete combustion. So we write out our formula and we are mindful of states of matter. So propane is a gas. You may not know some of these hydrocarbons, but so I'll tell you if you need it. We're going to react it with oxygen. So remember, oxygen is a diatomic. So it's always O2 and it is a gas. And then we're going to make CO2, and carbon dioxide is a gas, and we're going to make water, which is actually a liquid. And water gets formed in a combustion reaction in the liquid form, but it's so exothermic, it releases so much energy that it evaporates that water right away. So let me fix my 2 there. So we want to balance this. And what I tend to do is I would leave my oxygens to the end here because I have just an O2 molecule. I can balance that at the end. So I'll go down the list and I'll try to balance my carbons first. I need 3 of them. I'll put a 3 in front of CO2. I need 8 hydrogens. I already have 2 in front of water, so I'll put a 4 out front. 4 times 2 equals 8. And now I'll deal with my oxygens. So I have 4 here under H2O. I have 3 times 2, so plus 6. Add those up, total of 10. I need 5 oxygen molecules. The other kind of combustion is incomplete combustion. And this occurs when we do not have enough oxygen around to react. So remember, oxygen is only 21% of air. So if you don't allow a lot of air to get in with your fuel or your hydrocarbon, you're going to even have less than 21%, and you're not going to have enough oxygen to completely combust the molecule. So you start to make some extra products. Now, some of the products are the same. CO2 and H2O are exactly the same as it was in complete combustion, but you also make carbon monoxide and you also make carbon, or what we call soot. So visually, you can tell you have an incomplete combustion reaction because you're going to have an orange flame and you're going to see soot particles. Okay, and an orange flame is an indicator that you have soot. Okay, if you were to analyze the orange flame, you would actually see up close little black carbon soot particles dancing in that flame. That's what causes it to be orange. Here is an image that I thought was a little interesting. It's the combustion of a candle. We are exposed to candles and we use them a lot. So, just to give you a little bit of background info as to what's going on. Let's start at the top. The top of the candle is the hottest part. I think many people know that. You'll see some people, I don't do this, but run their finger through a candle flame and nothing happens. But hold your finger up here at just above the candle flame and it is extremely hot. Look how hot, 1400 degrees C, and you will burn your finger. The brightest part is where you have glowing hot soot particles. So there you go. These are little carbon particles that are super, super hot. So that's when you see something black like metal or coal and they start to burn like a white color, that's just indicating how hot they are. The arrow up is showing us that water vapor and carbon dioxide and carbon monoxide and soot, all 4 products of an incomplete combustion reaction, are being produced and they're moving upwards, okay? Because the heat, right, is causing all these particles to rise. If we have less oxygen right here, we see an orange color. And if we have the most oxygen down at the base of the wick, we see that blue color, which is indicating complete combustion. So kind of a nice little image that sort of, shows both types of combustion happening at the same time. So when we carry out incomplete combustion reactions, again, the reaction is the same all the time. Here's propane again. So we saw propane earlier. We did the complete combustion reaction for it. Here it is with the incomplete. So again, you're going to take your molecule, you're going to react it with oxygen gas, and then you get the same 4 products. The order of your products doesn't matter. Okay, so I don't care what you put first, as long as you have all 4 of them. And then we go through the exercise of trying to balance this. And sometimes this is a little bit trickier. And sometimes with incomplete combustion, you can get different coefficients to balance it, because all we need is we need to have not enough oxygen for complete combustion. Well, how much is not enough? Maybe you only have the tiniest bit of oxygen. Maybe you have a medium amount. Maybe you were so close to the complete combustion amount of oxygen, your coefficient is just slightly less than what it would be for complete. So you can have different coefficients here, and there's no right or wrong as long as everything balances. So I'm going to start to balance this one. And again, I'm going to start with hydrogen because there is only one place where I can balance hydrogen, which is over here with water, and I'm going to put a 4 down. I want to balance those carbons, and I need 3 of them, and I already have 3. They are all spaced out, but I have 3 over on the product side. And then now I run into a bit of a wrinkle because I have to balance my oxygens, and you have to be mindful of the whole odd, even numbers of oxygens in a combustion reaction. Over here, I have to balance with my oxygen gas on the reactant side, and it's an even number. So I have to have an even number of oxygens on the product side as well, and I don't right now. So right now I have 2 oxygens, I have another 4 over here, and then I have 1. So I have a total of 7, and I'm not interested in that. Okay, so when you're not interested in that, and I'm just going to erase some of these to make it a little bit cleaner. When you're not interested in those values, because you get this odd even problem, the quick fix is this. You go back to your fuel and you double it. Okay, and when we double it, we're going to now go back and we're going to take that 4 that was in front of water, and I'm just going to cross it out and put an 8 in there. So I have a total of 16 hydrogens. Now I need 6 carbons, and I am mindful that over here, there is a single oxygen that is causing me some odd even issues. So why don't I balance my carbons there in order to get the oxygens to be an even number. So if I put a 4 out front here, I'm going to now have 6 carbon atoms, right? I have 4 from carbon monoxide. I have 1 over here, that's 5, and I have 1 more over there, which is 6. Now let's balance my oxygens. I have 2 oxygens under CO2. I have 8 under water, and I have 4 associated with carbon monoxide. That is a total of 14. I can now come over to oxygen and balance it with a 7. So you just have to be mindful of that, and that sometimes that odd even situation happens in combustion reactions. Here's another one. Let's talk about butane reacting with, notice the wording, insufficient oxygen. So we're going to take our formula, C4H10. Butane is a gas. We're going to react it with some O2, which is also a gas. We're going to make our 4 products of incomplete combustion. So we're going to have CO2, which is a gas. We're going to have H2O, which is a liquid, and again, gets evaporated immediately from the heat. Carbon monoxide, which is a gas, and then carbon, which is a solid. So we're going to go along and balance this, and I'm going to get you to stop the video and try to balance this on your own. When you've got that figured out, come back and watch the rest of this to see if your coefficients match mine. So hopefully you've balanced that reaction, and I'm going to balance it now. Our coefficients might match, but they might not. Again, that's okay. In incomplete combustion, you don't have enough oxygen, but everybody can have different amounts of not enough. So I'm going to come over and I am going to balance my hydrogens with a 5 out front of water. I am now mindful that I have an even number of oxygens over here. I have 2 oxygens plus 5 plus 1. Okay, over there. So I have an even number. I don't want to mess that up because then I'll be allowed to balance my carbons that way. Balance my oxygens this way. So if I need 4 carbons, what I'm going to do, I need an extra carbon. I'm just going to come over here to the free carbon and I'm going to put a 2 in front. Now I have 4 carbons on my product side. And with those oxygens, I had 8. So I'm going to come over here and put a 4 in front of oxygen. So maybe your coefficients match mine. If they didn't, feel free to have me come by and check it out.